Good evening, everyone. My name is Jyoti Sharma, and this is lecture 4, week 4 live session. So let's start. Okay, so I will cover here the chemical kinetic mechanism, chemical kinetic reaction mechanism, chemical kinetic catalysis, and the part of the catalysis A, B, and C. So here we will talk mostly about the order of the reaction, then molecularity, how this molecularity is different from the order of reaction, and then we will talk about the catalyst. We do have different type of catalyst based on the different phases of the solvent and the nature of the catalysis. Then we will talk about the micelles as well, and then somewhat we will discuss about the nanoparticles. Let's have the first question, and my first question is, what is the correlation between the order and the molecularity of the reaction? So you people can give me the answer. So you people can give me the answer in the chat box. You people can communicate with me via unmuting yourself, and then I will see how many of the you are giving me the right answer. And then, but don't worry, I will correct you. Just give me 1 minute. Okay, so the answer for this question is no relation. And okay, so how we are giving the no correlation between the order and molecularity of the reaction is that, let me explain to you how this is possible. Let me get this. Okay, so if you people remember, in the last week we had a equation for this order of the reaction, and that equation was that this R. Uh, why this is getting removed? Let me change the pen. Okay, so this R is equal to we have uh, the concentration of A, and then the M, B, and here it is N, and some constant, that is K constant for the reaction. So here M plus N is giving you the order of the reaction. So and if I draw one balanced equation here, 1 plus B is giving you C plus D, right? So if it is giving you C plus T, and your reactant is A plus B, then the product of the concentration of your reactant and here the power is m plus n, and this m plus n you can't it is not just like that. Here it is 1, here it is 1, here it is 1. So this is not the stoichiometric coefficient, but this m and n we can calculate by the by performing some experiment, as we already have discussed it. We have some graph, and in that graph, if it is a first order, if it is a first order reaction, then what will be, it is the log of concentration and time, and then this will be like this, right? So based on the map, based on how it is increasing or decreasing, so just pardon me, it will be like this. This is not like this. If we have the log concentration, then this will be a straight line. But if we have just c and t, then this will give you the such kind of map, right? But if it is a log of the concentration, then this will give you the straight line, and based on that lines we can estimate whether this order of the reaction is 1, 2, or 0, or anything else, right? So this is how we can calculate this order. Molecularity is different. Molecularity is so for example, you have one reaction, this H2 plus O2 is giving you, let's say, H2O. And for example, this is just hypothetically, uh, if it is a 1, then this is also 1, and this is 1. And if we are assuming that H2 plus O2, the one molecule is colliding with another molecule of the O2, and after combining, it is giving you the H2O. Okay, but here just the assumption is that whatever the reaction is happening, it is happening in the one step. Okay, then only we can say this 1 and 1, this will give you the molecularity. Okay, but most of the time, what happens is that this H2 and O2 is giving you H2O, but it is not happening in the one step. It is taking multiple steps. So this is known as the complex reaction. If it is taking more than one step, and so each step is known as the elementary step. And in that elementary step, the number of molecules of reactant that we need will known as the molecularity. So molecularity and order is completely different to each other. So that's why the option we had, no correlation, positive correlation, negative, and highly positive. So among them, no correlation is the right answer. And so So, okay, let's see again. This is the order of the reaction. So, order of the reaction is the sum of the exponent of the concentration term in the experimentally determined rate law. And it can be determined experimentally and can be zero, fractional, or whole number. Okay, so just keep in mind, because we are calculating this experimentally, so this can be either zero or fractional or the whole number, and this we can apply to the elementary and the complex reaction. As already I have mentioned, elementary is nothing but we have the reaction, and that reaction can be performed in the multiple steps. So each step is known as the elementary reaction. Okay, so this can be applied to both elementary and the complex reaction. And here is just the example by which you can understand. So for example, we have a, that is the small letter a, that is the coefficient, stoichiometric coefficient. Then the one chemical species which is reactant, so a plus bb is giving you the product. Here we have the for the rate law. So rate is equal to, this is a constant, and then this is the concentration of the reactant raised to the power, and that power is giving the m and n. Okay, and this m and n is giving you the order of the reaction, and the overall order of the reaction will be m plus n. Just keep in mind, this m plus n is not equal to a and b. Okay, so that's why there is a no correlation between order of the reaction and the molecularity. Then if I go here, okay, so next is the molecularity of the reaction. Next is the molecularity of the reaction. So molecularity of the reaction is the number of reactant molecules involved in an elementary step. So just keep in mind, we have complex reaction. In that complex reaction, we have multiple steps by which we have to complete the reaction, and each step is known as the elementary step or elementary reaction. So if we are talking about the molecularity, molecularity is not just the stoichiometric coefficient. It is the number of molecule, reactant molecule we need in an elementary step. So for example, if we have, let's say again, H2 and O2 is giving you H2, right? And if we do balance here, this is one, this is one, and but here this, let's say, two, and here it is two. So this is the balanced reaction, right? So this is balanced reaction, and here the stoichiometric coefficient is 2, 1, and 2. So this is not the molecularity. Molecular, this is, if we will say like the number of molecules are 2 and 1, this is not the right, this is just the balanced equation. What we have to do is we have to see how this H2 and O2 is combining and giving you the H2O, how many step it is involving with, right? So and this can be anything. This is not just the balanced equation. So balanced equation is not giving you the molecularity, but in that balanced equation, the number of steps that we needed to complete the reaction, each step is the elementary step, and in each elementary step, how many number of molecules you need for the reactant is giving you the molecularity. Okay, so just balanced equation is not giving you the molecularity. So molecularity of the reaction is the number of the reactant molecules involved in an elementary step, and this is always whole number, cannot be zero or fraction, because we need number of molecules, and this number of molecules cannot be in the fraction, right? And cannot be zero. So that's why always if we are calculating this molecularity, this will be in whole number, and it is only determined for elementary reaction, not for overall complex reaction. As I told you, if we have one complex reaction and that complex reaction is H2 plus O2, this H2 plus O2 is the balanced equation only. Okay, we do not know right now how many steps we need to complete this reaction. Based on each step, we will determine the molecularity. So it is only defined for the elementary reaction, not for the overall complex reaction. And we can divide this molecularity into different types based on how many molecules we need of the reactant. If we need one molecule of the reactant, then we will call it as the unimolecular. So for example, if O3, this O3 is giving you O2 plus O. Okay, so this is one molecule of the reactant we need for the reaction to happen. So this is unimolecular fraction. If we need two molecule of the reactant, and that will give you the product, then we will call it as a bimolecular reaction. So this is N2 plus O2, and this is giving you the NO2 plus O2. So here we need two molecule of the reactant. Then we have the termolecular reaction. So here we need the three molecule of the reactant, and that will give you the product. Okay, so this is the type of molecularity you can calculate, but just keep in mind, molecularity is not as the coefficient of the balanced equation. This is the coefficient in the elementary steps. Okay, as we know, the one equation cannot be, it may be that it is not being completed into one step. If it is completed into two step, then in each step we need a number of molecule of the reactant, and based on that molecule, for the each step we will we can tell about the molecularity. We can't tell about the molecularity for the whole reaction. Okay, so this is how this molecularity is different from order of the reaction and the balanced equation, right? So if we do compare the order of the reaction and the molecularity of the reaction, then definition is order of the reaction is the sum of the exponent in rate law, as already I have discussed, right? Uh, Here, this m and n, this m and are not same to a and b, and this is giving you the sum of the exponent in rate law. This is order of the reaction. And if we are talking about the molecularity of the reaction, so these are the number of molecule involved in the elementary step. And how we can determine this order of the reaction? We can determine experimentally, but if we want to calculate this molecularity, then this we can calculate theoretical from reaction mechanism. Okay, then the if we are calculating the possible value, then order of the reaction can be zero, can be fractional, can be whole number, because we are just calculating it experimentally. But if you know that molecularity, so this is the number of molecules we need of the reactant, so number of molecules cannot be in the fraction, so it will be always in the whole number. So that's why this will be the whole number always. Then it can apply to both elementary and the complex reaction, and it will be only for the elementary reaction. And here is the example. So this is how from the graph only we can calculate the order of the reaction. So I think this is clear from this is clear. Now coming to the next question. So what is the correlation between the stoichiometric representation and the molecularity? The options are no correlation, positive correlation, negative correlation, and highly positive correlation. So what do you think? You can write in the chat box if you know the answer for this. What is the correlation between the stoichiometric representation and the molecularity? As I told you, so if it is the A and this A plus B, and B is giving you, let's say, C and C plus D plus D and D. So what it is talking about, it wants to know the relation between stoichiometric representation. So stoichiometric representation is nothing but this A, this B, this C, and D. And the molecularity, as we talked about, this molecularity is nothing but the number of molecules we need in an elementary step or in an elementary reaction. So can you right now tell me the correlation between coefficient representation and molecularity? It is positive, negative, highly positive, or there is no correlation? You can write in the chat box. Okay. So the answer should be no correlation. Again, there is a no correlation between order of the reaction and the molecularity. As per the question one, we got to know about this. The second is there is again no correlation between stoichiometric representation and molecularity. So let me tell you how. We have this stoichiometric representation, as I already have discussed. So these are the stoichiometric coefficient that represent the proportion of molecules involved in the overall reaction. So important point is it is the molecule that involved in the overall reaction. But if we are talking about the molecularity, then molecularity is the number of molecules involved in an elementary step or in an elementary reaction. Okay, so this can be different from the stoichiometric, and there is no any correlation between these two. So here, if we do have the example, H2 plus O2 is giving you H2O, and we are using two molecules of H2 that are reacting with the one molecule of O2, and this is giving you the two molecules of H2O. So this is the balanced equation. Here it is the stoichiometry, and this stoichiometry is not giving you the molecularity, because for the molecularity we have to see in how many steps this reaction was completed, and in each step a number of molecules we need of the reactant, that is giving you the molecularity. So here if we see, so for the molecularity of the reaction, molecularity refers to the number of reactant molecules involved in an elementary action. So this is not, as I already have repeated this is the single step reaction, and again it is a whole number, we already have discussed about this, and it is determined from the reaction mechanism, not the overall stoichiometric equation, and it applies only to the elementary reaction, not complex reaction. And again, we already have discussed about the classification of molecularity. It is, if it is one molecule of the reactant, then it will be known as the unimolar. If we have two reactant, then it is bimolar. And if we have the three reactant, and three reactant molecules, involvement of these three molecules is very rare, because the collision of three molecular simultaneously is a little difficult. Okay, so that's why this term molecularity is not very prominent, but it is the rare case. And okay, so I think the molecularity of the reaction, coefficient of the reaction, stoichiometric coefficient, and the order of the reaction, these three are different, and there is no any relation between these three. Okay, so I think from this point of view, it has been cleared, right? So I should move to the next. Okay, so there is also a table that is giving you the difference between stoichiometric representation and the molecularity of the reaction. So if we are talking about the stoichiometric representation, then this is the balanced chemical equation showing reactant and product in correct proportion. Okay, and for the molecularity of the reaction, the number of the reactant molecules in an elementary step. And how it can be determined, for the stoichiometry, it is by balancing the chemical equation, but for the molecularity, by analyzing the reaction mechanism. And for the stoichiometric representation, it is applies to both elementary and the complex, but as I told you, if we want to calculate the molecularity, then this will always be the elementary reaction, and this can be any real number, and molecularity will always give you the whole number. And this is one of the example from where you can learn. So okay, next coming to the next problem, and the next problem is what determines the order of the overall reaction. And I have four options: the molecularity of the reaction, the molecularity of the slowest step, the molecularity of the fastest step, and the stoichiometric coefficient of the balanced reaction. So you can give me the answer for this. What determine the order of the overall reaction? So for example, if you have one reaction, and that reaction is being completed using four step. Okay, in that four step your reaction is being completed. Okay, so how this order of the molecularity, order of the overall reaction will be determined? So you know that molecularity is for the elementary step. Okay, you can't calculate the molecularity for the overall reaction, right? So molecularity is the concept just for the elementary reaction. So what do you think, what should be the right answer for this? Okay, so the answer is B, that is the molecularity of the slowest step. So let me tell you, let me explain you this. So for example, you have one reaction, and that reaction is being completed in the fourth step, and three step are very fast, but one step is very slow. So let's say one step is taking almost 10 hours to complete, but the another three step are taking just 5 minutes, 5 minutes and 5 minutes to complete the reaction. Okay, so this slowest step will be the determining factor for this overall reaction. Okay, so that's why whatever the molecularity we have of the slowest step, that will determine the order of your overall reaction. So let's see how the, and if we are talking about the molecularity of the reaction, we understood it very well that molecularity is just applied. We can apply this molecularity to an elementary step or elementary reaction. This we can't apply to the overall reaction. So this is not the right answer, right? Then molecularity of the slowest and fastest, as I already have discussed, how the slowest step can be determining rather than this fastest step. Then in that previous question only, I discussed and I emphasized that this stoichiometric coefficient not not the molecularity, and there is no any correlation between molecularity, the stoichiometric coefficient, and the order of the overall reaction. So this will not be the answer. So let's see the answer. So B will be the right answer, the molecularity of the slowest step. So how this will be, just see. So in multi-step reaction, the step is one step is slower than the other, and this is known as the rate determining step, RDS. And the overall rate reaction is determined by the reactant involved in this slower step. Note the entire reaction equation. So that's why the answer will be molecularity of the slowest step. If we are talking about the molecularity of the reaction, as I told you, this is incorrect because molecularity applies to only an elementary reaction. Then fastest step, as I told you, fastest step cannot control the rate, but the slowest step will control the rate. And as again I told you, there is no any correlation between stoichiometric coefficient and the order of the reaction. So this will not be the answer. So finally the answer will be molecularity of the slowest step, right? So let's come to the next question. So the next question is, what does the activation energy of the of a reaction represent? So I have four options: the energy difference between reactant and product, the energy difference between the activated complex and the reactant for the forward reaction, the energy required to form the product from reactant, and energy released when the reaction reaches equilibrium. So what should be the answer for this? What does the activation energy of a reaction represent? So let me first tell you the graph. So for example, this is one graph, and so let's say this is the energy that reactant had already. Okay, so let's say this we can show by energy. That was the initial energy that the reactant already had. Then this is the activation energy. This is the activation energy. Okay, so AE. So this is the energy that we need to form the complex, and then this will go down. Let's see. From that graph, what we can tell is that this is the energy difference between the activated complex and the reactant for the forward reaction. And for the backward reaction, this will be the energy difference between the activated complex and the product. Okay, so this is the activation energy. So how much energy we need to form the complex, and this we can calculate how we will have some initial energy with with the reactant, and then the energy we need, so it will be the difference. So that's why this B should be the right answer. So B is the right answer, and let's explore more about the activation energy. So here, initially we have the energy of the reactant, then it will form some complex, and while forming that complex we need some energy, and that energy is known as the activation energy. And then we will like some product will be formed, and whatever energy the product will have, that will known as the energy of the product. Okay. And in the endothermic, because we know we need some energy, then this is the energy absorbed. And for the exothermic, we know some energy are released, then so here if we will see, this much energy will be released. So activation energy is the minimum energy required for the reaction to proceed, right? For forward reaction, EA is the energy difference, that activation energy is the energy difference between activation complex, that is the transition state, and the reactant. For the reverse, as I told you, this is the energy difference between the activated complex and the product. So that's why if we are talking about these things, let me clear this. So the energy difference between product and the reactant. So this is nothing but this is known as the enthalpy. Okay, this is not the activation energy, this is the enthalpy. Then B already we have selected. Then the energy required to form the product from reactant. No, this is not right. And the energy released. So how these are incorrect? Let's see. So A is incorrect because this describe the enthalpy change, not the activation energy. C is incorrect because it does not specifically mention the transition state. And D is incorrect because activation energy is unrelated to equilibrium conditions. So that's why B answer will be the right one. Let's go to another question. Which of the following statement about a catalysis is incorrect? So right now, what we are discussing is these are the similar question to the assignment questions, and we are trying to see what will be the right answer and why. Right. So the question is, which of the following statement about a catalyst is incorrect? And we have four options. The catalyst provides an alternative pathway with a lower activation energy. The B is it remains unchanged in mass and chemical composition after the reaction. The C is a catalyst increases the rate of reaction but does not affect the equilibrium position. And D is a catalyst starts a reaction that would not otherwise occur. So what do you think? What should be the right answer for this? Okay, so if we see each option one by one, then a catalyst provide an alternative pathway with a lower activation energy. This is the right statement. So let me again draw this figure. So for example, this is the energy reactant had, then this will make a complex, and then let's say this is your energy with the product. Okay, and this energy is the activation energy. So whenever we will have some catalyst, what it will do, it will reduce the activation energy. So now the activation energy is this much. So the energy that we need from the complex will be lower. So that's why it helps to increase the rate of the reaction, right? So this is right. Catalyst provide an alternative pathway with the lower activation energy. This is absolutely right. Then it remains unchanged in mass and the chemical composition after the reaction. This is again right, and how it is right. So for example, if we need if we are forming from water and oxygen, if the reaction is, it is giving you H2O2. So let's say water plus oxygen is giving you hydrogen peroxide. And if we have some catalyst here, okay, no doubt this catalyst will involved in the reaction. This will speed up the processing, but this will not be the change. This will not change in the mass and even the chemical composition after the reaction. So this is again the right statement. And then the next is, a catalyst increase the rate of reaction but does not affect the chemical equilibrium position. This is again right, because we already have talked this. The work of the catalyst is that it will increase or it will decrease the rate of the reaction. We will talk about this. Then it will increase the rate of reaction but does not affect the equilibrium position. Why it is not affecting the equilibrium position? Because the pace with which it is increasing the rate of reaction in the forward reaction will be equal to the pace with which the rate of reaction is increasing in the backward reaction. So that's why it will not affect the equilibrium position. The third is, fourth is, catalysts start a reaction that would not otherwise occur. No, this is not the thing. Whatever the reactant we have, that reactant should be compatible enough to make the product. Okay, it is not like that. If two reactant are not compatible to form the product, then catalyst can't do anything. Catalyst work is just to increase the rate of reaction. Okay, but initiation will be happen itself by the reactant. Okay, so this is the wrong statement. And the question was about the catalyst. The statement is incorrect, so D should be the right answer. So let's see the explanation for this. So a catalyst provides an alternative pathway. We already have talked about this. A catalyst work by lowering the activation energy of the reaction, making it easier for the reactant molecule to reach the transition state and form product. So this was the right statement. Then a catalyst participate in the reaction but is not consumed or permanently altered by it. So it will be recovered in its original form at the end of the reaction. So this is again the right statement. Third is, catalysts speed up both, as I told you, speed up both forward and the backward reaction, uh, and that's why this will not shift the equilibrium position. It only helps the system reach equilibrium faster. But here, the fourth option, a catalyst start a reaction that would not otherwise occur. This is incorrect, because a catalyst does not initiate a reaction. It only accelerate a reaction that is already thermodynamic feasible or compatible. And if the reaction is not possible due to unfavorable condition, high energy, because of high energy barrier or the lack of reaction, a catalyst cannot alone make this happen. Okay, so that's why D will be the right answer, because this is the incorrect statement. Okay, next coming to the another question, and this is, what does the turnover number represent in catalysis? So we have four options: the time required for a reaction to reach equilibrium, A B answer is the number of reactant molecule a single catalyst molecule can convert before deactivation. C is the number of reactant molecule present in a reaction, and D is the rate at which catalyst react with a substrate. So what will be the right answer for this turnover number? So what does this turnover number represent in the catalysis? So what do you think? Okay, so so this turnover number, uh, this is the number of the reactant molecule a single catalyst molecule can convert before deactivation. So for example, if you have one if you have, let's say, one catalyst, okay, and that catalyst is converting five reactant molecules into the product. Okay, so the turnover number will be 5, because this is the number of reactant molecules. So first we have to calculate the number of reactant molecule and then a single molecule. Okay, and then if we will divide that, then that will give you the turnover number. So let's see the explanation for this. So B is the right answer. So TON, this is a turnover number, is the measure of catalyst efficiency, because it is calculating how many cycle a catalyst can complete before becoming deactivate, and this we can calculate as the moles of the product formed upon moles of the catalyst used. Okay, we do have some numerical question, I think 2 or 3 based on this TON, and we will see how we can calculate this. Then A is the incorrect because TON does not depend on the equilibrium. C option is also incorrect because TON measure the number of reactant molecules converted, not just their count. And D option is also incorrect because TON is not a rate but a measure of total catalytic activity. So that's why your B answer will be the right one. Okay, let's move to the next question. So there is a relationship between turnover frequency and the turnover number, and how we can like, what is the relation between this? So the one is TOF is equal to TON multiplied by time. TOF is equal to TON divided by time. TOF is equal to TON plus time. And TOF is independent of TON. So how you will see the relationship between TOF and TON? So the answer B will be right. So if we want to calculate the frequency, then whatever the value of TON we have to divide it will be the time that will give you the TOF. Let me show you the answer for this. So B is the right answer. TOF, that is the turnover frequency, measure the rate at which a catalyst convert reactant into product. So this is the rate. So that's why the denominator will be time. So whatever TON we will have, that will be divided by the time, right? This TOF tells us how fast the catalyst operates. So for example, if catalyst is converting five molecule into the product, then but in how many time? Okay, so this will give you the rate. So how fast the catalyst is performing, is operating. So that's why the time is here in the denominator. uh So this is TON upon time, but it is not the multiplication, but it is the division. And it is again not added. And yes, there is a relationship between TOF and TON. So option D is also not the right one. So option B will be the right one. That TOF is equal to TON divided by time. Okay. So next move to the right. Next question. Okay, why TON defined per active site in heterogeneous catalysis? Option we have is because the exact number of catalyst molecule on the surface is difficult to determine. The B option is because heterogeneous catalysts do not participate in reaction. C is because heterogeneous catalyst dissolve in the reaction medium, and D is because heterogeneous catalysis follow first order kinetics. So there is a different definition of TON based on the type of our heterogeneous catalysis. Okay, so for example, if you have homogeneous catalysis, the definition of TN will be different. If this is heterogeneous catalysis, then this will give you the different definition. And if it is the enzyme based catalysis process, then the TON definition will be different. So what do you think? Why the TON defined per active site in heterogeneous catalysis? So here the right answer is A, because the exact number of catalyst molecule on the surface is difficult to determine. Um, so first you have to understand the different type of catalysis or the catalyst. So we have homogeneous catalyst. So what do you mean by homogeneous catalyst is that, so for example, if you have a solution and that solution is in liquid in nature, right? And if your catalyst is also liquid in nature, then this will known as the homogeneous catalysis. Okay, because the phase is same, liquid liquid. For example, if we have some reaction, or we want to have the reaction of the solid reactant, and we are using the solid catalyst as well, so this will give you the homogeneous because the phase is same, solid versus solid. But if it is the heterogeneous catalysis, for example, if we have the solution and that solution obviously is in liquid phase, right? And if in that solid or sorry, if in the liquid solution we need to put some solid catalyst, then this will give you the heterogeneous because the phase is different. The solution was in liquid phase, but the catalyst is in solid phase, so there is a disparity. So this is the heterogeneous catalysis, and the question is related to heterogeneous catalyst only. So why is TON defined per active site in heterogeneous catalysis? And here the answer will be because the exact number of catalyst molecule on the surface is difficult to determine. Let's see why this answer is correct. So, in heterogeneous catalysis, the catalyst is a solid surface uh, on which reaction take place. Okay, unlike homogeneous catalyst, as I told you about that, in the homogeneous catalyst, the phase will be same, where we can count individual catalyst molecule. In heterogeneous system, only surface active site participate. Okay, and that's why it is very difficult for us to calculate the TON. We already talked about what do you mean by TON. So this is kind of efficiency of the catalyst, how many number of catalyst we will use to perform, like how many molecules will be converted to the product based on per molecule of the catalyst. Okay, so this is TON. So based on that, B answer is the right one. Next, coming to the next question. How is TON measured in biocatalysis? The options are by counting the number of enzyme molecule in the reaction, by measuring the rate when all enzyme molecules are complexed with the reactant, by weighing the total amount of enzyme used, by determining the activation energy of the enzyme. So what do you think? What should be the right answer? Let me tell you what do you mean by this TON. Here in here we already have discussed about TON. So this is the catalyst efficiency. So number of how many cycle a catalyst can complete before becoming inactive. So this is something about the efficiency of the catalyst, right? So this is TON, that is the turnover number, right? And the another one was the TOF, and this TOF is nothing but the rate at which catalyst convert reactant into product. So this will be TOF is equal to TON divided by time. So these are the TOF and TON. So my question is like how we can calculate this TON in biocatalysis or enzymatic reaction. So what do you think? What should be the answer for this? How we can calculate TON, A, B, C, D. You can write in the chat box if you are comfortable enough. You people can also write. Okay, so B answer will be right by measuring the rate when all enzyme molecules are complexed with the reactant. As I told you, the TON will be different for different type of. Yes, Joshi, B is the right answer. So for different type of catalysis, so if whether it is homogeneous, whether it is heterogeneous, whether it is the enzyme based, so based on the type of catalysis we are talking about, TON will differ. So for the enzymatic reaction, it will be by measuring the rate when all enzyme molecule are complexed with the reactant. So this is how we can define. So here is the explanation. So for the biocatalysis, enzyme act as catalyst, and here TON can be defined as the number of substrate molecule converted when all molecule are bound to reactant, and this can be given as the rate of reaction upon total enzyme concentration. So that's why B is the right answer. Okay, next coming to the another question, and this is based on the catalyst. So what type of catalyst is used to slow down the decomposition of hydrogen peroxide and maintain its strength? We have four options: positive catalyst, negative catalyst, auto catalyst, and the enzyme catalyst. So what do you think? What should be the right answer for this? You can write in the chat box. You can speak like which should be the right answer for this. Thing is, so what is happening is that if you have H2O2 in a bottle, okay, and H2O2 is in bottle, and this is this will be decomposed into H2O, that is water, plus O2. Maybe at your home this hydrogen peroxide may be used for cleaning the teeth, and it is said that after some time this hydrogen peroxide solution will be changed into water and O2, and the effectiveness of hydrogen peroxide to cleaning the teeth will not be very much effective. So if we want to slow down the decomposition, so what kind of catalyst we need? Either positive, negative, auto catalyst, or enzyme catalyst. What do you think? What should be the right answer for this? Okay, let me tell you, if we are talking about the positive catalyst, then the work of positive catalyst is to increase the reaction rate. Okay, so if we have H2O2, then this, and if we are having some catalyst, that is the positive catalyst, then what this positive catalyst will do, this will increase the rate of reaction to change into H2O plus O2. Okay, If we have the negative catalyst, then whatever rate we had to change it from peroxide, hydrogen peroxide to water and oxygen, the rate will be slowed down by the negative catalyst. Okay, so positive catalyst is increasing the rate, negative catalyst is decreasing the rate of the reaction. Okay, then if we are talking about the autocatalyst, then autocatalyst is nothing. You have the reactant, and that reactant is forming some product. Okay, and that product is increasing the rate of reaction. Okay, and this is how this will your product is inducing or increasing the rate of reaction. Then this is itself, so it is itself increasing the rate of the reaction, so that's why this is autocatalyst. And enzyme catalyst means you need some enzymes, and enzymes are nothing but the protein. We have a lot of enzyme catalyst in our body that is performing, that is increasing the rate of the reaction. So for example, in your stomach you have the food, so some enzyme are working to increase the rate of the digestion. Okay, so these enzyme are the catalyst, but enzyme, right? Yes, B is the right answer. So yes, negative catalyst will slow down. If it would be the increment, then this will be the positive. But if it is the negative catalyst, then this will slow down, right? So I have some explanation about this. So if it is the positive catalyst, then this will increase the rate of reaction. Okay. If it is the negative catalyst, that will slow down the reaction. If it is the auto catalyst, then the speed, it will speed up the reaction by the product of the reaction only. Okay, and if it is enzyme catalyst, then we have a lot of enzyme, and that enzyme will enzyme will increase the rate of reaction or decrease the rate of reaction, right? So if it is using the help of enzyme, then this is known as the enzyme catalyst. So B will be the right answer. That a negative catalyst, that is also known as the inhibitor, because this will inhibit the reaction, right? And by increasing the activation energy, we already have talked about the activation energy. Again, I will talk about this into the next question. But if we are increasing the activation energy, it will be very difficult for the reactant to form the product. Okay, so this will increase the activation energy, or it can also block some active site, and that's why these are the inhibitor or the negative catalyst. So I think this is clear. I should go to the next question. Which of the following is an example of an autocatalyst? Fe3 plus ion in the oxidation of oxalic acid by acidified KMnO4. Magnesium dioxide in decomposition of hydrogen peroxide, vanadium pentoxide in the contact process, nickel in the hydrogenation of vegetable oil. What do you think? What should be the right answer for this? We are talking about an autocatalyst, and I already have mentioned, let's say you have a reactant. Okay, so actually A answer is the right one, and let me tell you why. So first understand what do you mean by autocatalyst. So for example, you have A plus B, and that is giving you, let's say, C. Okay, so initially this A and B will form the C, and this C will increase the rate to combine this A and B and to form the C again. So this is the autocatalyst. So your product itself will increase the rate of the reaction. And this is happening here in this oxidation of oxalic acid by acidified KMnO4. So what will happen if we have the reaction of oxalic acid and acidic KMnO4? This will form Fe3 plus ion, and this Fe3 ion will enhance the rate of the reaction. So this is autocatalyst. this manganese dioxide in the decomposition of hydrogen peroxide. As I told you, now hydrogen peroxide will decompose into H2 and O2, right? H2 plus O2. And this manganese dioxide, this manganese dioxide is not the product. So for an auto catalyst, your catalyst will be your product itself, right? So this is not the answer. Then again, in the contact process, this vanadium pentoxide is not the product, and nickel is also not the product. So that's why A is the right answer only. Let me explain in better way. So in the redox reaction, Fe2 plus ion are initially formed as the intermediate, which further catalyze the reaction by accelerating the oxidation process. And this is the classic example of autocatalysis, right? And here we talked about this, right? Hydrogen peroxide is giving you H2O plus O2, and manganese dioxide is just the positive catalyst, the external catalyst. It is not the product. Then contact process, what happened in the contact process? We have oxidation of S2O to SO3, and that again will give you the sulfuric acid. But in that we need vanadium peroxide, that is the positive catalyst, right? But it is not the autocatalyst. Then nickel, this is again the positive catalyst but not the autocatalyst. So you should have know the difference between positive catalyst, negative catalyst, then autocatalyst, and the one is induced catalyst. Okay, so I think it is clear why this A answer is the right one. Next, coming to the next question. So what is the role of lead compound in the catalytic oxidation of SO2 in the contact process? So as I told you, what do you mean by this contact process? So this is for the formation of sulfuric acid. And if we want to form the sulfuric acid, we need to have the oxidation of SO2. Okay, and for that catalytic oxidation, we need some catalyst. Okay, that will increase the rate of the reaction, that will take less time to form H2SO4. Okay, so what is the role of lead compound? Whether it is a negative catalyst, whether it is a positive catalyst, whether it is a catalyst poison or catalyst promoter. What do you think? What is the right answer for this? You can give me wrong answer as well, because I will correct you. Don't worry about this. You can write in the chat box, you can speak. What do you think? What is the role of lead compound in the catalytic oxidation of SO2 in the contact process? So we already have talked about negative catalyst. So what negative catalyst will do? This will reduce the rate of reaction. Okay. Positive catalyst, this will increase the rate of reaction. Catalyst poison. So we have catalyst, and again we have another compound. That compound can inhibit the activity of the catalyst. Okay, so for example, if a catalyst is increasing the rate of the reaction, but if we will put some catalyst poison, so that will inhibit the activity of the catalyst, and that will slow down the rate of the reaction. Okay, so this is catalyst poison. And catalyst promoter, it may be that because with the help of catalyst, we are able to achieve the product within, let's say, 10 minutes. But we can add some catalyst promoter that will enhance the activity of our catalyst. And based on that activity, we can complete our reaction within, let's say, 5 minutes. So the compound, that compound will enhance the activity of the catalyst or the catalyst promoter, and the compound that will inhibit the activity of the catalyst will be known as the catalyst poison. And we already have talked about it. So the lead compound is nothing but the catalyst poison. So C is the right answer. And let me tell you how. I have the explanation for this. So LAD compound, either it is PBO or this is PBS. This will deactivate the vanadium pentoxide catalyst. So we have one catalyst, that is vanadium pentoxide, that increases the oxidation rate from SO2 to SO3. But if the rate we have, if we need to deactivate this catalyst, then we need some catalyst poison, and that catalyst poison are LAD compounds. Okay, these compounds bind to the active site of the catalyst, preventing it from facilitating the oxidation of SO2 to SO3. And these are catalyst poison or anti-catalyst. So that's why C is the right answer. Negative catalyst is not the right answer, because negative catalyst is directly decreasing the rate of reaction. Okay, and these LAD compound do not just slow the reaction, but they completely deactivate the catalyst. Positive catalyst, it cannot be. And then the catalyst promoter, this is again not the right answer. So C is the right answer. Yes, C will be the right answer. Let's come to the next question. Which of the following statement is correct for the exothermic reaction with high activation energy for the forward reaction? Options are: the reaction proceeds rapidly at room temperature, the reaction require a catalyst to occur at a reasonable rate, C is product have higher energy than the reactant, and D is activation energy for the reverse reaction is lower than that for the forward reaction. So what do you think? Which statement is correct for the exothermic reaction with high activation energy? Okay, so Joshi gave me C answer. So, okay, let me tell you about the exothermic reaction. So, uh, let me give some time. And so, uh, this is the exothermic and endothermic reaction, right? So we have initially the energy with the reactant. Okay, so this is, let's say, energy of the reactant. Then this reactant will form some complex, intermediate complex, and to make the complex we need the energy, and the difference between this complex and the energy of the reactant is the activation energy. Okay, and if it is the endothermic reaction, then because we know in the endothermic reaction energy we have to absorbed. Okay, and if energy is being absorbed, then the energy of reactant and energy of the product, so see here the difference, the energy of product is higher than the energy of the reactant. Okay, but this is not the case for the exothermic reaction. Again, we need the activation energy to form some complexes, but here energy will be released. So can you see the energy of the reactant is more than the energy of the product? Okay, so that's why C answer, that answer where it was like that, the energy of product is higher than the reactant. So this is not right, because here the energy of reactant is more than the energy of the product. So let's come to the question. Mm, Let's come to the question we had. Where were we? So we were here, right? So B is the right answer, because we need catalyst to occur at the reasonable rate. We already have talked about this. The product have lower energy than the reactant. Okay, so B is the right answer. And the reaction proceeds rapidly at room temperature. It may or may not be possible, because for the exothermic, uh, like it may or may not be possible. Then the activation energy for the reverse reaction is lower than the forward. No, activation energy is almost same for this. So let me show you the explanation for this. So the reaction rapidly proceed rapidly at the room temperature. No, because we need large amount of energy for this process. Okay, to start. So this is not the right answer. Then yes, we need catalyst to occur at the reasonable rate, because let's say this is we already have seen this is the exothermic, and if we have some catalyst, then what this catalyst will do, this will reduce the activation energy. So this is the work of the catalyst, how catalyst works. So this will reduce the activation energy, and because of that your rate of reaction will be fast or higher. So this is right answer. Then this is incorrect, because we talked about this product have lower energy, and this is again incorrect. So that's why B is the right answer. I think this is clear. Should I go to the next question? Okay, if a diagram show the energy profile for the chemical reaction, so what that diagram was? That diagram was like either this one, or let's say that diagram was this one. So this is for exothermic, and this is for endothermic, right? So, and this is the energy profile of the reaction. Which point on the diagram represent the transition state? So options are the starting point of the reaction. So what do you mean by starting point? So this is the starting point. What represents the transition state? Starting position, then the highest peak, this is the highest peak, the ending position, this is the ending position, and the difference between reactant and product energy. So this one. So what do you think? Which point on the diagram represent the transition state? What do you think? What should be the right answer for this? Transition state, as I told you, we need to form some complex, and that complex are intermediate. And so for example, we have the reactant. That reactant will combine and will form some temporary or intermediate complex, and for to form that complex we need activation energy. Okay, after forming that complex we will form the product. Okay, and this will give you the energy of the product. So the activation energy we need to form the complex here. Okay, and these complex are temporary in nature, that are intermediate. So the answer is the highest peak on the energy curve. The one person is giving me the answer as soon as I explained the why the answer should be B or C, and then that person is giving me the right answer. But it is okay. This is good. At least you are giving me the answer. Okay, so let's see the explanation for this. So the starting point, the reactant are at the initial energy level in the diagram, and this is not showing you the transitions, because transition occur at the highest energy point. So B is the right answer. Ending, the product appear in the final energy. So this is again not the right answer. And the difference, as I told you, the difference between reactant and product is enthalpy change. Okay, so B is the right answer. I think this is clear. Okay, next coming to the question. In the process of potassium iodide and oxygen, Fe3 is reduced to Fe2, and simultaneously iodide ion are oxidized to iodine, that is I2. This reaction is an example of what? Inhibitor catalysis, enhancer catalysis, induced catalysis, and autocatalysis. What do you think? What should be the right answer for this? We already talked about inhibitor catalysis and enhanced catalysis. So inhibitor catalysts are very similar to like negative catalyst. So negative, what is the work of negative catalyst? To slow down the rate of reaction. Enhancer catalysis, so this will increase the rate of reaction. Induced catalysis, um, this I will discuss, and then autocatalyst we already have discussed that there will be the one product, and that one product will catalyze the reaction itself, and that will give you the right answer. But here, if we are talking about, so what is happening is that this Fe2, this Fe3 is reducing in Fe2, right? So as soon as this reaction will happen, so this will initiate another reaction, that is to oxidize I minus to I2. No, the answer will be induced, and I'm telling you why. So the first step will will lead to the next step. So this is induced catalyst. So one formation of one step, or formation of the product of a one step, is inducing to increase the rate of reaction of the second step. Okay, so if Fe2 is changing into so Fe3 is changing into Fe2 plus, then this change will will induce the increment in the rate of reaction for this I minus to I2. So that's why this induced catalysis is the right answer. So I have explanation too. It might be that you are confusing with the autocatalyst, but autocatalyst is you have one product, and that one product is increasing the rate of the reaction itself. But here we have first step, so from Fe3 to Fe2 plus, and this Fe2 is increasing the rate of reaction for I minus to I2. So this is induced catalysis. So let's see the explanation for this. We already have talked about the inhibitor, so this catalyst slow down or prevent the reaction. Enhancer, so this is to modify the efficiency of the original catalyst. This will increase the rate of reaction. Induced is one reaction initiate another. So if there is a reaction that this Fe3 to Fe2 minus, then this reaction will initiate another one. So that's why this is the right answer. And if it is the autocatalyst, the product of the reaction itself acts as the catalyst. I know this induced and auto is relatively similar, but not exactly the same. So here, neither Fe2 plus or N2. So these are the products, right? These products are not catalyzing the reaction. So that's why this is not the autocatalyst, but the one reaction is initiating the another. So that's why this is the induced catalysis. I think this is clear. Okay, next come to the next question. So there is the one reaction, Ostwald process, for nitric acid synthesis. So here NO is used as a catalyst in the formation or in the oxidation of ammonia to nitrogen dioxide. So this is the example of what? Heterogeneous catalysis, homogeneous catalysis, biocatalysis, or micellar catalysis. As we already have discussed, the classification of catalyst, either it is homogeneous or heterogeneous, is based on the phase. So for example, your reactant is in liquid in phase, and if your catalyst is also liquid in phase, then we will call it as the homogeneous. If your reactant is in solid in phase and your catalyst is in liquid in phase, so there is a disparity, the phase is different for the solution or for the reactant and the catalyst. If there is a disparity in the phase, then this will be the heterogeneous catalysis. Okay, biocatalysis is nothing but the enzymatic catalysis. So we need enzymes for the to increase or decrease the rate of the reaction. Micellar, we will talk about this micellar as well. So there is tail and head, the hydrophobic and hydrophilic, and that will increase or decrease the rate of the reaction. So what do you think? What should be the right answer here? Heterogeneous, homogeneous biocatalysis, or micellar catalysis? I think right now you can give me the answer because I already have explained the things. Just see nitrogen oxide, ammonia, and nitrogen dioxide. So can you check the phase of these three compound? If the phase of these three compound are same, then we will call it as the homogeneous. If the phase is not phase is different, then this will be the heterogeneous. But we know that nitric oxide is not the biocatalysis, because biocatalysis is made up of the biomolecules, and this nitric oxide is not the biomolecules. My slide is not appearing. Is it not appearing for everyone, or my slide is not appearing, everyone? Can anybody tell me my slide is visible to you or not? Because the person told me like my slide is not appearing. Is it appearing, right? There may be some problem with you guy. I can see the this is showing the slides are visible. Okay, okay. Okay, so now tell me what should be the answer. So answer will be homogeneous, because as I told you, if the phase of your reactant and your catalyst is same, then this will make the homogeneous. Okay, if sometime it is happening now, like your reactant is in liquid phase but your catalyst is in solid phase. Let's say can you give me the name of one or two, that is vanadium and all? So these are solid in nature, but your reactant is in liquid phase. So if there is a disparity, then this is the heterogeneous, but if there is no any disparity in the phase, then this is the homogeneous. And here nitric oxide, ammonia, and nitrogen dioxide are same in phase, so that's why this is the homogeneous reaction. Here is the explanation. So for heterogeneous catalysis, the catalyst is in different phase than the reactant. For example, we need iron in the Haber process for ammonia synthesis. So iron is in solid phase, but this N2 and H2 is in a gaseous phase. Okay, in homogeneous reaction, the catalyst and reactant are in same phase. So either all gas or all liquid. Okay, so in Ostwald process, this NO is the gas, and that is working as the catalyst, and that will do the work of catalysis to do the oxidation of NH3, that is ammonia, to NO2. Okay, and both and these three are in gaseous phase, so that's why this is the homogeneous. Biocatalysis, as I told you, we need the biological catalyst, and NO is not the biological catalyst. So this is not the right answer. And micellar catalysis occur in the reaction when surfactant enhance rate reaction, and this is not the surfactant. NO is not the surfactant, right? So that's why B is the right answer. I think this is clear. Next, move to the next question. So, Paul and John developed 12 principles of green chemistry in 2000. Which of the following statement is true or is or are true? So, design for energy efficiency, use safer chemical and solvent, minimize the potential for accident, all of the above. What should be the right answer? So what do you mean by green energy? So green energy is something like that. The focus is on the sustainability. Okay, so sustainability means whatever you will do, you will not harm the environment. And to reduce the negative impact of the chemistry, the green chemistry was developed. And there are some principles that we need to follow. Yogi gave me D answer. And let me see another answer. Okay, yes, D is the right answer because you people know that from that for the transformation, let's say we are transforming A to B or B to D or C to D, uh, some energy are lost as a heat. Okay, so we need such kind of reaction that are very energy efficient in nature. Okay, so this is right because as more energy will be transformed into heat, this is not good for us. This is not the sustain, this is not come under the sustainability goal, right? So then use safer chemical and solvent, yes. Minimize the potential for accident, yes. So that's why all of the above will be the right answer. So you people can search out what are the 12 principle for this green chemistry, and this all of the above is the right one. Okay, I already have discussed you about heterogeneous and homogeneous catalysis. So you have to tell me which example is giving you the heterogeneous catalysis. So for option we have hydrogenation of vegetable oil using nickel catalyst, oxidation of ammonia to nitric oxide using platinum catalyst, decomposition of hydrogen peroxide using manganese dioxide, and all of the above. As I told you, if the phase of your reactant and the catalyst is different, then this is heterogeneous. If the phase is same for this reactant and the catalyst, then this will give you the homogeneous catalysis. You know the phase of the catalyst, nickel catalyst, platinum catalyst, and the manganese catalyst. Is it in solid or it is in liquid phase? Nickel is a solid, right? Platinum is also solid, right? Manganese dioxide is again different than hydrogen peroxide. So the phase is different in every case. Most of the time here, vegetable oil is liquid in nature. This is solid in nature. Ammonia is ammonia to nitric oxide is gaseous in nature. Platinum is solid in nature. Hydrogen peroxide is liquid in nature, and this is again solid in nature. So the phase of the reactant and the catalyst is different, and that's why all of the above should be the right answer. So D is the right answer. I already have discussed everything about you. Nickel is in solid, then platinum is again solid. Manganese dioxide is solid catalyst, and this ammonia, vegetable oil, and hydrogen peroxide are liquid in liquid, and this is in gaseous nature. So all of the above are the example of heterogeneous catalysis. Okay, we have two or three numericals only, and these numericals are very nice actually. So here, what we have the concentration of pesticide, and we need to degrade that pesticide because we know that pesticide has the negative impact. So we want to degrade the pesticide with the catalyst. Okay, and we use the dose of the catalyst of 1 gram per liter, and the reaction took 2 hours. So can you calculate the turnover frequency of the catalyst? So what you have to do is, first you have to calculate the moles of the reactant. Okay. After that, calculating the moles, you will go to the calculation of the molecules of the reactant. Okay. So you will have the number of molecule of catalyst. You have number of the molecule of the reactant. You will divide that and you will get the turnover frequency. So we already have discussed about this turnover frequency. So this is and divide by the time. So what was that turnover efficiency? Is firstly we have the TON, that is the turnover number, and turnover number is per molecule of catalyst how many reactant we can change into the product. Okay, so this was the TON, and when we will divide it with the time, then this will give you the turnover frequency. So firstly, we should have the number of molecules of the reactant, then we will divide it with the number of molecules of the catalyst, multiply by the time. That will give us, and that will give us the turnover frequency. So let's see how we can calculate this. Okay, so if we need to calculate the moles of the pesticide, so the concentration is given, that is 50 mg per liter. So from that concentration, if we will divide that concentration by molecular weight, that will give you the number of moles, and molecular weight is also given. So the moles of pesticide is nothing but the concentration divided by number of by molar mass. Okay, then if we want to calculate the number of molecules of the pesticide, then you have to multiply it with the Avogadro number. Okay, because per mole there is 6.0 023 into 10 raised to power 23 molecules, but we have this much number of moles. Okay, so we have to multiply so that we have the total number of molecule of the pesticide. So if we will multiply this mole to the Avogadro number, that will give you the number of molecule of the pesticide. Then we need time into the second, then we will multiply it with the 3600, that will give you the time in second. And then the job is almost complete, because we have the number of molecules of your reactant, then the dose, and multiply by the time taken, and this will give you the how many molecules of the reactant we can degrade, we can decompose per gram of your catalyst per second. So this is how we can calculate this TOF, that is the turnover frequency. So this is 1.20 into 10 raised to power 16 molecule of the reactant per gram of the catalyst per second. So this is how we can calculate this. I think this is clear. So should we go to the next question? Okay. Which of the following is used as a catalyst in the contact process for the sulfuric acid synthesis? So you have to tell me the positive catalyst, because if we need to need to do the oxidation from SO2 to SO3 and then formation of the sulfuric acid, we need some positive catalyst, right? And you have to tell me what catalyst we do use in the contact process for sulfuric acid synthesis. So options are iron oxide, vanadium pentoxide, copper sulfate, and zinc oxide. So what do you think? Which catalyst we use in the contact process for sulfuric acid synthesis? Because the oxidation is very slow naturally at the room temperature, but if we want to increase the rate of the reaction for the formation of sulfuric acid, we need some catalysis, and we need some catalyst. And can you tell me the name of that catalyst we need? Venkat Rao gave me answer C, that is copper sulfate. But the answer is vanadium pentoxide. It is all right. Every time you can't remember the catalyst because we have thousands of reactions. For example, we have the Haber process, we have the contact process, and a lot of reactions. We have a lot of process, and for each process, like it is not mandatory to know the catalyst that we use, but whenever you have a need, you should know what kind of catalyst we will use in that kind of process. So it is all right. So the answer is vanadium pentoxide is the catalyst that we need in the contact process for the sulfuric acid synthesis. So if you see, this iron oxide is used as a catalyst in Haber process. So, and Haber process for the ammonia synthesis. Okay, and this is not used in the contact process. So if this is iron oxide, then this will be used in the ammonia synthesis process, and that process is known as the Haber process. Okay, vanadium pentoxide, yes, for sulfuric acid synthesis, vanadium pentoxide act as a catalyst to speed up the oxidation of the sulfur dioxide to sulfur trioxide. Okay, and this is very crucial step. So this is the right answer. Then if we are talking about the copper sulfate, no, copper sulfate is not involved in the contact process. And then zinc oxide, this is again not involved in the contact process. So this vanadium pentoxide is the right answer. So should we go further? Okay. So again, we have one question related to turnover number. Here it is not turnover frequency, but it is a turnover number. So if we have compound Y that have the concentration of 5 micromolarity is completely degraded in the presence of catalyst at the dose of 5 gram per liter, and you need to calculate turnover number of the catalyst. As I told you, whenever you will divide the turnover number with the time, that will give you the turnover frequency. But this is turnover number, so you will not divide it with the time. So again, we have to calculate the number of moles of the reactant, and then based on number of moles, you will calculate the number of moles of the reactant, and then it will divide by the dose of your catalyst. Okay, and because this is turnover number, then we need not to divide it with the time. Okay, so this is how we can calculate this turnover number. So let's see how we can calculate this. So we have the molarity of your reactant, that is 5 multiplied by 6 raised to power 10 raised to power minus 6, and we also have the molecular weight, that is 250.5 gram per molar. Based on that, what we will do, we will calculate the number of moles. So what we will do, we will divide multiply the what we have to do is, so we know that how we can calculate this number of moles from the molarity, and then we will multiply this with the Avogadro number, and this is how we will get the number of moles of your reactant, right? And then we know the dose of your catalyst, and whenever we will divide this number of molecule by dose of the reactant, that will give you the TON. So I think this is clear. Should we go further? And if you know, here molarity is nothing but the number of moles per liter of the solution. And molarity, we can also, this is given mass upon molar mass and upon liter. So this is the molarity. So from that molarity, you have even molar mass. You can calculate the number of moles, and after that, you have to multiply it with the Avogadro number so that you have number of molecules. Then you will divide your number of molecule with the dose of catalyst so that you have TON, that is the turnover number. So I think this is clear. Should we go further? Yes, let's go. Which of the following theory provide the most accurate explanation for the mechanism of the heterogeneous catalysis? So as I told you, heterogeneous catalysis means your reactant phase is different from your catalyst phase. So which theory provides the most accurate explanation? Collision theory, surface theory, transition state theory, and the adsorption theory. What do you think? What should be the right answer for this? Okay, if it is a heterogeneous means most of the time our catalyst is in solid in phase, right? And our reactant is either in gaseous phase or liquid in phase. Okay, so what will happen? Your reactant will be absorbed. Sorry, your catalyst will be absorbed by the reactant. So that's why here this adsorption theory works. And let me explain it another way. Okay, so uh, let's know every theory one by one. So if we are talking about the collision theory, then this theory explain how the frequency and energy of particle collision affect the rate of reaction, and this is not specifically addressing the role of catalyst, right? So this is not the right answer. Surface theory focus on the interaction of reactant with the surface of the catalyst. Okay, and this is not widely recognized or comprehensive as the adsorption theory. So this may be the right answer, but this is not very much comprehensive theory. So this will not be the right answer. And then the transition state. So this explain the energy profile. We had one question related to that. Then we come to the adsorption. So adsorption theory explain the mechanism of heterogeneous catalysis by focusing on how reactant molecule adsorb onto the surface of the catalyst, and the adsorption of the molecule on the active side of the catalyst increase their reactivity that will facilitate the reaction, and this theory provide a more accurate and detailed explanation of heterogeneous catalysis mechanism, and that's why this D answer is the right one. I think this is again clear. Should we go further? Okay, this question is related to the nanoparticles. So if we have the boiling point of bulk water, that is 100 degrees Celsius, what would be the boiling point of water in the form of nanoparticle? So if we have water but in the form of nanoparticle, so how this boil point will be changed? So either so options are the boiling point will be same as it was, that is 100 degrees Celsius. It is greater than 100 degrees Celsius, very low, maybe even below 0 degrees Celsius, and none of the above. So what do you think? If we will change this water in the form of nanoparticle, how this will have the impact on the boiling point of the bulk water? A, B, C, D. You people can write answer in the chat box if you know, and even if you do have some like approximation in your mind, if you are having some logic in your mind, then based on that you can also write your answer in the chat box. Okay, so the answer is very low, maybe even below zero. So this is the advantage of nanoparticles. So the property of nanoparticle may be completely different. Yes, C is the right answer. So the property of the nanoparticle of the same molecule can be very much different uh, from the molecule that is not in the form of the nanoparticle. So Here the boiling point may be very low, and that may be well below 0 degrees Celsius. So this is the advantage of nanoparticle. That's why there is a lot of research of this nanoparticles, and the nanoparticle and how this nanoparticle can help us for the medical purpose as well, because the property is completely different. So let me show you the answer. As I told you, nanoparticle of the water exhibit different physical property, and that will change significantly the boiling point. Okay, so this will not be the 100 degrees Celsius. Uh, while certain phenomena can increase the boiling point under specific condition, but most of the time, water in nanoparticle often behave differently due to surface effect and change in the physical property, and that will lead to the lower boiling point than the higher one. And this one is the right answer, that is very low, and none of the above is not the correct answer. So very low. Nanoparticle of the water exhibit drastically different behavior, and this can lead to the significant decrease in the boiling point. Okay, so that's why C is the right answer. Okay, so we have some question related to micelles. So both detergent and soap in water share some common property. Which of the following is true for both? They are both non-biodegradable. They are both large hydrophobic molecules. They both lower the surface tension of water. They both increase the surface tension of water. What do you think? What is the same common property of detergent and soap? What is which is true for both? We know it answer. We know the answer of this, right? If we go to the first one, they are both non-biodegradable. No, this is not the right answer, because the one is degradable and the another is non-degradable. Detergent is non-degradable and soap is biodegradable. Right now, we have some changes, they both are now biodegradable. Uh, they are both large hydrophobic molecules. As I told you, we like here is the concept of micelles. So we have one head and tail. Head will give you, let's say, hydrophilic, and tail will give you the hydrophobic. So no, this is again not the right answer. Then both lower the surface tension of water. This is the right answer. They both will lower the surface tension. The role of detergent and soap is just to lower the surface tension of the water so that the dirt can be removed. Okay, so if we have the lower surface tension, that will help us to remove that dirt and to dissolve it into the water. So that's why C is the right answer. They both lower the surface tension of the water. So here see, some detergent may be biodegradable. Soap are typical biodegradable. And right now, both detergent and soap are biodegradable. If we are talking about hydrophobic, then this is not true, because uh, uh, they have the hydrophobic tail. Okay. Then they both lower the surface tension, yes, and because of that, this property, lower the surface tension, this property help in cleaning by allowing water to spread more easily and emulsifying oil and dirt. So this is the useful property of detergent and soap, and this is incorrect, because the work of soap and detergent is to decrease the surface tension of water. Okay, so C is the right answer. Okay, coming to the next question. So this is the surfactant. Okay, so this sodium dodecyl sulfate is the surfactant, and you have to tell me what kind of surfactant it is. It is cationic surfactant, anionic surfactant, then zwitterionic surfactant, and non-ionic surfactant. I know you it is not very easy to remember each of these things, but like this is just a question, and you can give me the answer for this. So let me tell you the answer for this quickly. So this is the anionic surfactant, and let me tell you about this. So, sodium dodecyl sulfate is an anionic surfactant, meaning it has a negatively charged sulfate group in its hydrophilic head. So that's why this is anionic, and this negative charge make STS effective in cleaning and emulsifying oil and dirt. So that's why this B answer is the right one. Yes. Okay. At what concentration do surfactant molecule typical form micelles in an aqueous solution? Above the critical micelle concentration, much below the CMC, very low concentration but a high temperature at any concentration. So what do you mean by micelle? Micelle are nothing but you have head of your surfactant, and then here we have the tail. So such kind of, if such kind of circular things the surfactant makes, then this is known as the micelles, and this help in lowering the surface tension of the water, and that's why the reaction can be happen easily, so that dirt can be removed. So the answer is above the CMC. So if we have the above the CMC concentration, this will a surfactant molecule will form the micelles, right? So A is the right answer. Okay, A is the right answer. Okay, the next question is what must occur for the chemical process to proceed effectively? Options are the pressure of the reaction mixture must decrease, the energy of the reactant molecule must be lower than the activation energy, the energy of the reactant molecule must reach or exceed the activation energy, and the temperature of the reaction mixture must be lowered. What do you think? How we can increase the rate of the reaction? Yes, C is the right answer. The energy of the reactant molecule must reach or exceed the activation energy. As I already talked about this, we have the energy of the reactant. Then to form the complex, we have to achieve the activation energy. Okay, and then the product will be formed. So you have to reach up to the activation energy. So if your energy of the reactant, if you will add some energy to the energy of the reactant, and this will reach either to the activation energy or uh, exceed the activation energy, then your product will be formed. Okay, so C is the right answer. So I'm not going into detail, but because we already have discussed much about the activation energy, let's go to the next question. Okay, which of the following theory is used to explain the mechanism of homogeneous catalysis? So homogeneous means your catalyst and your reactant is in same phase. So adsorption theory, lock and key theory, intermediate compound theory, and surface mechanism theory. What do you think? What should be the right answer for this? Okay, so let's see one by one. Adsorption theory is for heterogeneous catalysis, right? Because Adsorb means we have the solid surface, and on that solid surface something will be attached. Okay, so this is adsorption. This is for heterogeneous catalysis, but not for the homogeneous catalysis. So this will not be the answer. Then lock and key theory. So this theory is mostly for the enzymatic catalysis. So it is something like your reactant have a shape just like the lock, and your catalyst have the shape like the key, and when they will combine, it will make the complex, and then this will form the product. So your reactant and your catalyst will have the same like lock and key. Okay, so each catalyst will have different kind of structure as different key, and each product will have some different type of structure, like as we have seen in the lock. So this is this is the example for the, this is the theory used for the enzymatic. Okay, then the intermediate compound theory. Yes, this is the right answer. Why? Because in the homogeneous, what will be happen, we have the catalyst, we have the reactant. This will form, this will attach to one another. Okay, and but if we know, like the original form of the catalyst will be maintained. Okay, so what will be happen, temporarily reactant will attach to the catalyst. Okay, but this will form the product, and this will be released, catalyst will be released in the initial form. Okay, so this is nothing but the intermediate compound theory. So the right answer will be C. Then surface mechanism, this is again not the right answer, then C is the right answer. And let's see. So see here, adsorption is for heterogeneous. Lock and key is for the enzyme catalysis. Intermediate. Intermediate theory is used to explain homogeneous, where the catalyst and reactant are in same phase. In this theory, an intermediate complex is formed between the catalyst and reactant before the reaction proceeds to completion. Okay, and this surface theory again is the theory for the heterogeneous. So C is the right answer. This theory is for the homogeneous catalysis. Okay, which metals are commonly used as catalyst in catalytic converter? So iron and copper, platinum and rhodium, zinc and nickel, magnesium and aluminium. So what happens is that in the vehicle, if you know, in vehicle we use the fuel, right? And when we do the combustion of this fuel, uh, carbon dioxide is released, NO2, that is nitrogen dioxide is released. So what we do, we use some catalyst. So for example, if the combustion is not completed, you have diesel or petrol, and if you are ignite, and this ignition is giving you the combustion. Okay, and if the combustion is not completed, then in spite of CO2, it can release CO, that is the carbon monoxide. So in spite of carbon dioxide, it is giving you the carbon monoxide, and you know the carbon monoxide is very dangerous. So the work of catalytic converter is that with the help of catalyst, it will change from CO, that is the carbon monoxide, to carbon dioxide. Okay, so this is very important because this CO2 is very dangerous as comparison to the carbon dioxide. And if you people know that the efficiency of carbon monoxide to bind with the hemoglobin is approximately 200 times more as comparison to the binding capacity of oxygen to bind with the hemoglobin. So whenever you will have the oxygen and the carbon monoxide, and the carbon monoxide will attach or will bind to your hemoglobin, and that's why you will have deficiency of oxygen in your body, and that will be very detritus for your health, right? So that's why whenever in the incomplete combustion in the vehicle, if CO is releasing, then by the use of catalyst, we will use some catalyst that will change this carbon monoxide to CO2. So what kind of catalyst we need for such kind of reaction? So B is the right answer. So we use platinum and rhodium as a catalyst in the catalytic converter. So B is the right answer. So catalytic converter in automobile use platinum and rhodium as catalyst. This metal help harmful gases such as carbon monoxide, NOx, and hydrocarbon into less toxic substances such as CO2, N2, and H2O. And that's why platinum and rhodium is the right answer, right? Okay. The next is, why is alumina used in catalytic converter? We talked about catalytic converter, right? We need platinum and rhodium. But why do we use alumina? So we have option: it react with the exhaust gas to neutralize them. It acts as a spotting material, increasing surface area for the catalyst. It speeds up combustion in the engine. It prevent rust formation in the exhaust system. So alumina is something like what we can do is enhancer. So whatever Chini, can you mute yourself? Let me. Okay. So this alumina is used as an enhancer. So we do have catalyst, but to increase the efficiency of the catalyst, we will use some another compound. So alumina is the one of that compound. So this act as a spotting material, increasing surface area for the catalyst, right? So this is used as the honeycomb mesh sport for platinum and rhodium, and this will increase the surface area so that this will allow the exhaust gas to stay, and so that it will come into contact with the catalyst, and so that your dangerous gases can be converted into non-dangerous gases. Okay, and if you people know, like most of the time there is advertisement that we have now petrol that are unleaded in nature. So in our petrol, the lead has been improved, lead has been removed. So why this unleaded petrol used in automobile with catalytic converters? Because this can poison. So we talked about this now, poison catalyst. So catalyst poison. So what the catalyst poison do? They can block the activity of the catalyst. Okay, so the activities of platinum and rhodium can be inhibit by the lead. Okay, so the answer A is the right. That is, lead can poison the catalytic converter by blocking active site. Okay, so let's complete this in 1 or 2 minutes. So we already have discussed this. This is something very much similar. Mm, let me go to some important question. Okay, why are nanoparticle effective as catalyst? Because nanoparticle have high surface area to volume ratio. So that's why this is very effective as the catalyst. So A is the right answer. This is not important. Then what is the function of active site in an enzyme? So this bind to the reactant molecule selectively. These are some question on enzyme. You can go through my slide and you can see answer and the question that I already have made. So this is how let's complete this. Thank you. I think because time is up and um, I can take your more time. So no, we finished this. So thank you so much. If you have any query, if you have any question, you people can tell me. You people can mail me anytime if you have the queries on jyoti21 at the rate iiscrb.ac.in. And if you have any kind of suggestion how I can improve this live session, you can also suggest me the change. I will definitely take into care the suggestion that you will suggest me. And again, we will meet Monday from 6 to 8. If you have any problem, if you have any suggestion, you can tell me. Otherwise, um, you can go and you can leave this call. Thank you so much.